Hello guys, my name is Simona and today I'm going to teach you how to get an A+ in organic chemistry. Yes, you. If I can do it, so can you. And in this video, I'm going to be covering the fundamental concepts that you must understand to excel in this course. But before I get into the content, you and me both, we have to leave our egos at the door because today we're going back to the basics. This video will be composed of 3 parts. In part 1, we are going to be discussing periodic trends. In part 2, we are going to be discussing nucleophiles and electrophiles. And that will lead us into part 3, where we will go over arrow pushing by looking at a very simple reaction. With that said, I gotta say it, don't forget to leave a like, comment, save, or subscribe to my channel if you like my content and want to support moi. But enough with the YouTuber stuff, let's get into the content, the chemistry content. So let's get into chapter 1. We will be talking about periodic trends. Consider a periodic table. The first periodic trend we are going to be discussing is electronegativity. Electronegativity increases from left to right across a periodic table. And what this means is that atoms that are found at the rightmost side of the periodic table are going to be more electronegative than atoms that are found to the left. So for example, a bromine, a halogen, is much more electronegative than a carbon. And oxygen is also more electronegative than a carbon. How I want you to think about electronegative atoms is that they are thieves of electrons. They are going to steal electrons from any atom that is nearby them. So for example, if a bromine is attached to a carbon, the bromine will be sucking electrons towards itself. And as a result, the electrons are going to be shifting towards the bromine. So bromine is going to be gaining more electrons, becoming electron rich. So the carbon is going to be losing electrons, becoming electron poor. In organic chemistry, we denote electron rich as delta minus, so electronegative. And a way to think about what is happening to the carbon atom, so the atom attached to the electronegative atom, is that it is going to be in a deficit of electrons. If you lose electrons, you become cationic. So this can be denoted as delta plus. Now we must think of electrons as a currency, just like money in real life. When atoms gain more electrons, they become negatively charged. So this would be like gaining more money in real life. And when they lose electrons, they become cationic. So this would be like losing money in real life. An easy acronym to remember this is LECGen. So lose electrons become cationic, gain electrons become negative. Let's relate this concept to a real life situation because believe it or not, atoms are just like human beings. They behave the exact same as us. Consider a robber. He goes and steals $1 million from the safe in a family-owned store. He leaves with it and he is never caught. He runs off to America and he lives the rest of his life as a rich man. But unfortunately for the family that he stole the money from, they're now in a huge deficit of cash. They might even have to close down their business. They became poor. Whereas the robber who left with the cash went on to live a very happy life without remorse for what he did to the family-owned business. That is exactly what happens when bromine is attached to a carbon atom. Bromine will steal all of the carbon's electrons without any remorse for what he's doing to the carbon. He does not care that the carbon is going into an electron deficit and becoming electron poor. All he cares about is the fact that he just got really rich. So I've mentioned the words electron rich and electron poor, so let's discuss what I mean by that. Knowing what electron rich means and what electron poor means is an essential concept in this entire course, and I will mention this term over and over again, so let's talk about it. So what does it mean to be electron rich? When an atom is electron rich, it means that it has excess electron density. So for example, like the bromine attached to a carbon in the last example. A way to identify an electron-rich atom is to look for an atom with lone pairs or pi bonds. If an atom has a lone pair, it can use that lone pair to go and attack something. Because in organic chemistry, to be able to move electrons, you must have them in the first place. And later in this video, we are going to refer to this as a nucleophile. And we'll go over what a nucleophile is and some very basic examples of them. An example of an electron-rich species could be the oxygen, a part of water, or ethene. The pi bond can flick out and grab an electropositive atom, just as the oxygen, a part of water, could use its lone pair and go and attack a hydrogen, for example, and become H3O+. Electron-poor atoms are atoms that are in an electron deficit, so for example, like the carbon attached to the bromine in the last example. Another example of an atom in an electron deficit would be the carbon, a part of a carbonyl. Oxygen is an electronegative atom, so it will suck electrons towards itself and leave that carbon attached to it in an electron deficit. So a carbonyl carbon is very easily attackable by a nucleophile. Now this leads me into topic number 2, which is discussing nucleophiles and electrophiles. The term nucleophile means nucleus loving. So nucleophiles love things that are like the nucleus. So what's like the nucleus? We must think of the nucleus as a positively charged entity. So if nucleophiles like positively charged entities, well, it likes positively charged things. So nucleophiles which are minus charged, or they have excess electron density, maybe they are neutral, but they might still have a lone pair, or it might be a pi bond, will use those electrons to go and attack something that is positively charged or delta plus because they love the nucleus. Nucleophiles love the nucleus. So nucleophiles love positively charged or delta plus things. Some examples of nucleophiles include anions, such as the hydroxide anion, so OH-, as well as neutral molecules, such as water that I mentioned previously, where it would use its lone pair to go and attack something delta plus, most likely a hydrogen. And finally, another example of a nucleophile is compounds that contain pi bonds, so ethene or ethine. Those pi bonds can flick out and grab electropositive things. For example, when ethene is reacted with HBr, the pi bond will flick out, grab the H, 2 in, 2 out, leaving a positive charge on one of the original carbons, a part of the double bond, and Br- is also produced. And since opposites attract, the Br- will go and attack the positively charged carbon. So now the double bond is removed, and you now have a hydrogen attached to one of the carbons and a bromine attached to one of the carbons. And this all stemmed from the fact that a pi bond acted as a nucleophile and attacked a delta plus H. Electrophiles, on the other hand, are going to be atoms in an electron deficit. So for example, such as the hydrogen in HBr in the example that we just went over. Another really good example of an electrophile are going to be atoms with a delta plus charge. For example, a carbon attached to an electronegative atom, such as a bromine, or a carbon a part of a carbonyl. Now, believe it or not, we have pretty much covered already half of the things you need to know to get an A+ in this course. Every single question stems upon these concepts that we have just discussed. But now, this has led me into my third concept, which is talking about arrow pushing. Before we get into the actual question, let's consider a waterfall. Pretend a very rich person decided they wanted to give away their money, and they stood at the top of the waterfall and they put $100 bills in plastic bags, zipped them up, put them into the waterfall, and let them go down and pool into the waterfall pool below. And pretend we have another person that's just a random poor little hiker that's on a walk on a Sunday. They come across the bottom of the waterfall and they find all these $100 bills. That person at the bottom of the waterfall now becomes very rich. Now, like I said previously, we must look at electrons as a currency. So if the electrons in this story were represented as the money, electrons will always start at a very rich atom and they will flow towards the more electron poor atom. Because the hiker at the bottom of the waterfall at the beginning of the story was a poor man until he stumbled upon the cash that was given to him by the rich man at the top of the waterfall that actually had the money. So in this example, we are highlighting the fact that electrons flow from electron-rich atoms, and they flow towards electron-poor atoms because opposites attract. Hence, nucleophiles need to have electrons, just like the rich man had cash, to flow and put the money into a place that did not originally have it. In chemistry, this is just like a nucleophile attacking an electrophile. The nucleophile originally had to have money to start the electron flow and attack something that did not originally have electrons, something delta plus or positively charged. Now let's go over a real example and highlight the arrow pushing. In organic chemistry, arrows are used to depict the flow of electrons, where electrons are always going to start flowing from something with electrons, so a nucleophile. An atom in an electron deficit cannot initiate pushing electrons because it does not have electrons. To start pushing electrons, you must have them. So we always start our first arrow at the nucleophile. This is going to be the most electron-rich atom in the reaction. So here we have NaCN. Whenever you have Na, it is just a charge balancer, forget about it. We must focus on the Cn. The Cn is going to bear a minus charge, hence it is nucleophilic and it wants to go and attack something that is delta plus or positively charged because it is nucleus loving, so it loves positively charged things. And opposites attract. Negatively charged things love positively charged things. On our other species in the reaction, we have a carbon attached to an iodine. Iodine is electronegative, so it will be sucking electrons away from that carbon, leaving that carbon in a delta positive state. Therefore, the Cn-, it is going to initiate the electron flow since it has the electrons, and it is going to attack the delta positive carbon center. And now, in most cases in organic chemistry, we are going to flow arrows via 2 in, because on the Cn-, we are using 2 electrons, 1 lone pair, to flow and attack the delta positive carbon, so 2 in. And now I say 2 out because that iodine is going to take the 2 electrons that were originally in the carbon-iodine bond. So we see the iodine has 3 sets of lone pairs, so 6 electrons around it. When the iodine takes the 2 electrons a part of the Ci bond and it goes 2 out, the iodine is going to end up with 4 lone pairs, so 8 electrons total, and become negatively charged. Now, the first arrow that started at the lone pair on Cn- and attacked the delta positive carbon will become a bond. So if you draw an arrow from a lone pair to a delta positive atom, that becomes a bond. And if the arrow starts between 2 atoms and goes up, out, and onto an atom, so for example, the iodine 2 out arrow, the bond will break, and those 2 electrons will then be a part of a lone pair in the end of the reaction. So let's do a little summary of what we learned in the arrow pushing chapter. Number 1, the head of the arrow points to where the electrons are going to end up. Number 2, arrows starting at a lone pair indicate a nucleophilic attack. Number 3, arrows that start at bonds and end on an atom represent the breaking of a bond and the formation of a lone pair on the atom that took the electrons. And in the question we went over, that would have been represented by the iodine taking the 2 electrons, a part of the original bond, and then becoming minus charged. Now, I hope that makes sense because visualizing how electrons move is the most important concept in all of organic chemistry. So if you are confused, please leave a question down in the comment box below and we can talk about it and I can make another video. Now, I'm going to end this video here, but do not worry, I'm going to make a part 2 where I will discuss resonance and other concepts such as how to visualize molecules in a 3D space, which is going to be very important when it comes to drawing Newman projections. But before I go, let's summarize everything that we talked about today. In chapter 1, we discussed how electronegative atoms are thieves of electron. This is going to create a dipole moment where electronegative atoms are going to become electron rich, and the atoms directly attached to them, such as a carbon, a part of a CBr bond, will become delta positive and end up in an electron deficit and be electron poor. We also learned in part 2 that nucleophiles are nucleus loving, they're also electron rich, and they are going to attack electropositive or fully positively charged atoms because opposites attract. Nucleophiles love the nucleus, so they also love positively charged things. They are going to attack positively charged things. And in chapter 3, we talked about arrow pushing and how the arrows are going to start flowing from the nucleophile, the electron-rich atom, and they're going to flow towards the electron-poor atom, and electrons flow via 2 in, 2 out in most reactions in organic chemistry, except for radicals, but that is a separate conversation and will be a separate video. I hope this video helped. Let me know if you have any questions, and I hope you have a great day. You've got this.